Okay, so it's 2:30, so let's get started. So this is continuing the structure formation series. Yesterday we spoke about inflation and how initial conditions are generated, and I was giving a brief discussion of Gaussian random fields. So this is the example that we were looking at yesterday, and how in a Gaussian random field, which is defined using these equations, the Fourier modes of the field, which are, so the field is zeta of x, and the Fourier modes are labeled by wave numbers k. K's are vectors, and the zeta k's are complex numbers. And these Fourier modes satisfy these properties where the real and imaginary parts are Gaussian random numbers with some variance, which is written as p zeta of k, which is called the power spectrum. And equivalently, you can think of these modes as being written as amplitude times a phase, where the amplitudes are exponentially distributed and the phases are uniform. So in this case, for example, you have some low k wave numbers giving rise to this configuration. And then if you add higher k wave numbers for this particular choice of power spectrum, you add some small scale wiggles, right? But the overall feature remains the same. So this is an example of a Gaussian random field. So I will continue this discussion today and speak about non-Gaussian fields before going on to actual structure formation. But before we begin, I just want to mention that there are a number of other online resources available for lectures on cosmology in particular. So a couple of years ago, some of us had organized a meeting at ICTS in Bangalore. So if you just go to Google and you type ICTS 2019 cosmology, it will take you to a web page of a meeting called Cosmology the Next Decade. And there you will find an entire, it's a complete set of lectures on various aspects in cosmology. Okay, so not just these introductory lectures that we are giving you here, but also much more details about state-of-the-art observations, state-of-the-art simulations, how you can connect theory to observations, and various other details. And the lecturers there were among the top researchers in the field. Several of us at IUCAA had also given lectures there. So I encourage you, if you're interested in the cosmological aspects of this summer school, that is an excellent resource. Okay, so you can go and just look for it. And all the videos of those lectures are available on YouTube. And if you go to the webpage of ICTS, they will give you the links to these lectures. So anything that I, for example, don't cover here, you will almost surely find covered in some of the other lectures there. So I want to highlight a couple of the series there. One is the structure formation series. I was giving those lectures. Another series which is useful for us, and I will not be able to cover any of it in detail, is the one on galaxy formation and evolution, which was delivered by Professor Kandaswamy Subramanian of IUCAA, and those lectures are also on the YouTube channel there. Okay, so let's come back to this. And of course, if you have questions for me here, feel free to ask in the Google form or as chat. And if we have time, we can also take some questions by unmuting people later. So I will keep this in this non-full screen mode because this is the end of the previous talk, and then I want to switch to the next talk after this. Okay, but there's just a couple of slides left here anyway. So we saw Gaussian random fields here. But we would also like to study these random fields in more generality because as you will see soon, the fields produced, the distribution of matter produced by structure formation is not Gaussian. So then you can ask, what does it mean for a field to be non-Gaussian? And actually it can mean anything, because if you go back to these equations, the thing that is highlighted in red or blue is the definition of a Gaussian random field. So any field whose Fourier components obey these properties will be a Gaussian random field. So anything that is not obeying these properties is therefore by definition a non-Gaussian field. That is not very useful, but there is a way of using these ideas to think about certain classes of non-Gaussian fields. For example, these are two non-Gaussian fields that are shown here. And what is highlighted here is the role of the phase correlations between them. Okay, for each field, the phase correlations are different from a Gaussian random field. So let me just switch back. Remember, for a Gaussian random field, we said that the phases are uniformly distributed and independent. So if either of these conditions is broken, For example, if the phases are not uniformly distributed, uniform means it's a flat distribution between 0 to 2 pi. If that is not the case, if there is a shape of the distribution, for example, or if the phases corresponding to two different wave numbers k and k prime, suppose those phases end up becoming correlated with each other. In either of these cases, the field will not be Gaussian. So here is an example of a field in which the phases are distributed differently, but the amplitudes are distributed identically. Okay, so in the left, I think it is the result of either a semi-analytical model or a full-fledged n-body simulation. It is probably a perturbation theory calculation here, but it has produced some distribution, and that distribution has a certain power spectrum P of k. The right-hand panel shows you another distribution which has a power spectrum which is almost the same as the power spectrum here, but clearly it looks nothing like this distribution, right? Visually, these two are very different. And remember, again, going back, actually, I should have just put these equations here. So remember that this is the amplitude of the field. And when I take the power spectrum, I am basically taking zeta k, and then I'm multiplying with a complex conjugate of zeta k prime. But k prime is forced to be equal to k if I want something non-zero. So this p zeta of k can be thought of as taking expectation value of the modulus of zeta k the whole square, right? So zeta k times zeta k star will give you p zeta k here after expectation value. But remember from your standard complex analysis that when I take the mod squared of a complex number, I am just taking the square of what I call its amplitude, right? Because ak squared is nothing but mod zeta k squared. So when I say that p zeta k is the same for the left and right panel in that image, what I'm actually saying is that the amplitudes are the same for those two fields, for the different Fourier modes in each of the two fields, but the phases are not. And this image shows you therefore the importance of the information contained in the phases. So different phase information can lead to very different looking fields, although both of them may have the same power spectrum. And this you have to remember if whenever somebody tells you that we will use the power spectrum as a probe of cosmology. Okay, this is actually something that is routinely done. Power spectrum is a probe of cosmology. But whenever you think in the context of structure formation, you have to remember a plot like this, that these two images have the same power spectrum, but they look nothing like each other. So just knowing the power spectrum is not enough to tell you about structure formation. Okay, although power spectrum is an important tool. Here is another example. In this case, the left-hand panel is a result of a full n-body simulation, similar to something I was showing you right at the beginning of the previous lecture. And in the right panel, something interesting has been done. So you take this simulation, okay, and you calculate the Fourier mode. So you can put a grid on this box, and you can calculate the density inside every grid cell. And then it's a uniform cubic grid, so you can apply standard Fourier techniques and get the Fourier transform of this density field. And then this Fourier transform, every Fourier transform coefficient will have an amplitude and a phase. So what has been done in the right-hand panel is that once you get the amplitudes and phases corresponding to every Fourier mode, you just scramble the phases. Okay, so a particular Fourier mode with a wave number k1 had some phase phi k1, and some other wave number k2 had some phase phi k2. For example, I picked k1 and k2 at random, and I just exchanged the values of their phases. Okay, I can play such a game with arbitrarily chosen pairs of wave numbers. Or I can just say that instead of whatever phase distribution I had for this field, I'll just assign randomly some uniformly distributed number between 0 and 2 pi for every mode. And then I will get some other field in Fourier space, and I can inverse Fourier transform that. Okay, and what is shown here is such an exercise, inverse Fourier transform of a field with scrambled phases. And you can see that it has become completely different. This is closer to what we were looking at as Gaussian random fields. Okay, for example, when you look at the CMB temperature map, it sort of looks like this. This is also not a Gaussian random field because the amplitudes here are correlated in a certain way, and it is not obvious that the amplitudes, so they are not necessarily exponentially distributed, because this is a non-Gaussian field. So in order to know whether this is a Gaussian field or not, you have to also ask whether the amplitude correlations here were the same as for a Gaussian field. They need not have been the case. But again, this is just a way to emphasize the importance of phase information in large-scale structure. And you can see here that this is the result of an n-body simulation with all of these nice filamentary web-like patterns that I was talking about in the beginning also. And when you scramble the phases, all of that has gone away. Okay, so this is just to highlight that it is the phase information which encodes the nature of the cosmic web. And therefore, these phases are very, very interesting things. So I think that is all I will be saying about phases in this series of talks. But it is good to keep these pictures in mind. So basically what the end of the previous lecture, the summary is that inflation creates initial conditions for the rest of the evolution of the universe. And these initial conditions generate density fluctuations or potential fluctuations, which are encoded by this gauge invariant curvature perturbation in the metric. And because of the coupling to gravity, these perturbations in the curvature of the metric will get transferred into the density of radiation and matter. And this is the thing we see when we look at the cosmic microwave background temperature field in the sky. Because when you remove the mean, that is the overall homogeneous isotropic mean of the temperature, and you remove the effect of our local motion towards the Virgo cluster, what you will end up seeing is tiny fluctuations like this. The amplitude of these fluctuations is of the order of 10 to the minus 5 in dimensionless units. So delta T over T is of the order of 10 to the minus 5 RMS. And these are the tiny fluctuations which are the seeds of large scale structure, and they are the remnants of inflation. Okay, so inflation happened, these seeds were generated, and then these seeds eventually led to structure formation. So I saw maybe this is a good time to take a couple of questions, because I will now, sorry, did I see, I thought I saw a question. Okay, maybe not. So in case you have something to ask, can you ask right now regarding anything about yesterday's lecture? You can raise your hands also if you like. We can spend a couple of minutes on this. Otherwise, let me stop sharing. And, there is a chat. Sorry, yes. So if you could tell when all these bodies in n-body concept, what are these bodies in n-body concept? Some uniform aspect. I don't entirely understand the question, but in today's lecture, I will be dealing with structure formation, and at the end of the lecture, there will be discussion of n-body simulations. So maybe you can wait until then. And sorry, what has happened? Okay. Sagar, are you there?
Yes, sir.
Can you see structure formation number 2?
Yes, I can.
Okay, so if you can hold the question about simulations until the end, and then if it's not answered, please ask it again. Okay, so this is a simulation that I showed you before. This is how we believe structure formation progresses in the universe. Tiny, almost uniform density perturbations start growing under the influence of gravity, and they form this web-like pattern. Okay, so today's lecture is going to discuss some of this, some of the aspects related to this formation of the cosmic web. And it will be a very broad brush introduction. Like I said, there is no time to actually go into detailed derivations. And in fact, if you really want to understand the details, there is no, alternative to actually sitting down and solving all the equations yourself. So at least for the first part of this talk, whatever I'm saying, if you're interested in understanding the mathematics, you should pick up Dodelson's book from the literature list that I had given earlier. Okay, so what I'm going to discuss in today's lecture, I will spend some time, around 15-20 minutes, on the notion of length scales and how length scales behave in the expanding universe. And this is going to be very important in order to understand how structure evolves. So then after this discussion of length scales, I will talk about what is called the linear regime, because I said that the initial conditions for structure formation have very tiny perturbations. And these perturbations, when you plug into the equations that you need to solve, you can linearize these equations. Basically, you do a Taylor expansion and you keep only the first order terms because these perturbations are very small. And that simplifies the equations considerably. Instead of solving partial differential equations, you end up solving ordinary differential equations. And we will see these ordinary equations that one has to solve. But then the interesting thing is at later times when these linear perturbations start growing and their amplitude becomes large enough that you cannot think of them as small perturbations anymore. And that's the regime of nonlinear growth. And then you have to, if you want to progress analytically, you have to make some very drastic approximations. So we will study some of these approximations, which have been extremely useful in the literature in building intuition and also in developing the field quite a bit. So the spherical collapse and the Zeldovich approximation. And at the end, I will talk about full-fledged numerical simulations which evolve the equations pretty much exactly. Okay. So let's start with this discussion of length scales. So remember our discussion of inflation, where we said that inflation is this period in the early universe. The reason to have this period was that we want points in the sky which are apparently causally disconnected. We actually want them to be causally connected because otherwise we cannot explain the fact that the CMB temperature is so uniform from one end of the sky to the other. Okay, and inflation did that for us. And the way it accomplished this is by saying that there should be a brief period in which the Hubble parameter is approximately a constant. Okay, so that's the typical way in which inflation progresses. That is not the only way in which you can solve the problem, but it is the most popular one. Okay, so what I'm showing here now is a plot. It's a schematic plot, but on the x-axis is the log of the scale factor. So the scale factor is increasing as a function of time. Okay, so I can use it as a clock. It depends only on time. So instead of time, I can use scale factor as my clock. And I am showing, I haven't put any numbers here, but this axis is supposed to represent the log of the scale factor. So it's a log plot, and x-axis is the log of the scale factor. And the y-axis is the log of some physical length in the problem. And we will talk about a few of these different lengths that we would like to study. So some physical length in the problem, okay, and I'm taking a log of that. So now on the x-axis, I can mark off some interesting epochs. For example, here schematically, I'm showing you the period during which inflation is active. Okay, and during this period, as I said, the Hubble parameter is approximately a constant. So C times H inverse is also approximately a constant. So I am using units in which C is equal to 1. So you can think of this H inverse as being the Hubble radius, remember, right? C by H was the Hubble radius. And during inflation, the Hubble radius is approximately a constant. So I have shown that as this horizontal line, just a schematic, some value. Okay. And therefore, for the entire duration that this line is approximately horizontal, I understand that this is the time where inflation is active. Now, at some point, inflation ends. Okay, and in this schematic diagram, I have shown it as a sharp truncation, but in reality, it could be some smooth transition that happens. And after inflation ends, then standard cosmology is supposed to take over. For example, if inflation ends around 10 to the 15 GeV or so, right after that, when the universe is at 1 GeV, for example, this is a scale, this is a temperature scale that we understand, and we know that Big Bang nucleosynthesis must have been active around that time, protons must have been forming and so on. So the universe should have been radiation dominated around this epoch after inflation, because we have very strong constraints that this must have happened. So in this schematic picture, instead of worrying about the details of this transition, I've just shown you a sharp transition that inflation ends and then a radiation dominated epoch begins, in which, if you remember, the Hubble parameter behaves like 1 over a squared, because the density of radiation behaves like 1 over a to the power 4. And the Friedman equation says that Hubble squared is equal to the density of the universe. Okay, the sum of the densities of the universe. Curvature is not there in this picture. And anyway, we are saying that the universe is radiation dominated. So the dominant component for the source of h squared is the radiation density, which is 1 over a to the power 4. So h behaves like 1 over a squared. So h inverse behaves like a to the power 2. So in this log plot, I have shown this as a straight line with a slope of 2. Okay, log of H inverse versus log of A will be a slope of 2. And this situation progresses until matter starts dominating. Okay, so early universe has radiation domination here, but then later universe has matter domination. And you also know when this transition happens. Again, it is actually a very smooth transition. I have shown it as a sharp truncation here at the radiation matter equality. So you have seen in, hopefully in the basic cosmology course, what this radiation matter equality epoch means. It is basically when the density of radiation is equal to the density of matter. And you can calculate this if you know the values of omega m, omega r, and that's it, right? So these two numbers tell you when this epoch should have happened. And let's say it happens at the location of this vertical line. So after this, the universe becomes matter dominated. Again, I'm schematically showing this as a sharp truncation. So remember, during matter domination, the Friedman equation says as h squared will be now the matter density, because that is the dominant density component. Matter density is 1 over a cubed. So h is 1 over a to the 3 halves. Okay, so that's a to the minus 3 halves. So h inverse is a to the plus 3 halves, and plus 3 halves is less than plus 2. So this line here has a slope which is slightly smaller than this line here, right? This is a slightly steeper line than this one. Okay, so that's all I have done. The red line is just showing you the evolution of the Hubble radius as a function of time, starting from inflation into the radiation dominated epoch and following into the matter dominated epoch. And later on there'll be a dark energy density dominated epoch when again this thing will turn over and start approaching a constant. But right now we are not really interested in that for the sake of this argument. So what is it that is now interesting? The thing that is interesting is to ask, if I take a particular co-moving wavelength for a perturbation that I want to study. Remember, we would like to study perturbations in Fourier space by decomposing them into wave modes. And the amplitudes of these wave modes are the things that are the variables of interest. And right now I'm asking about the wavelengths of these wave modes. Okay, so every wave mode comes with an amplitude and a wavelength. Amplitudes we will study in a little bit. Right now I'm interested in the wavelengths corresponding to these sine waves that form the Fourier components of my field. So I am showing you 3 different co-moving wavelengths: lambda 1, lambda 2, and lambda 3. Okay, and because I have chosen lambda 1 to be bigger than lambda 2, which is bigger than lambda 3, they are ordered in this way because I'm showing log lambda over here. So each of these, so the highest one corresponds to the largest wavelength. All right. And why is this line then not a horizontal line? It is because I said I want to focus on co-moving wavelengths, which are ordered like this. So the physical wavelength corresponding to each co-moving wavelength will be just that co-moving wavelength multiplied by the scale factor. Right? That is how physical wavelengths are defined in the FLRW metric. So what I will get here for each of these wavelengths is a straight line, because I'm doing log. So this straight line will have a slope of 1, right? Because lambda, the physical lambda, will be proportional to A. So each of these lines will have slope 1, and their amplitudes will be different depending on which wavelength I'm talking about. So the highest wavelength will have this amplitude, the lowest wavelength will have this amplitude. All of them will increase with time in this way. So now this is a very interesting plot, because as you can see, these 3 different wavelengths, or these 3 different wave modes, their wavelengths are either above or below this red line, depending on which epoch you look at. So if I look at this particular wavelength, right, it is increasing like this. In these epochs, its value was less than the red line, clearly. For these epochs, its value is bigger than the red line. And then again, its value becomes less than the red line here. Okay, so this is the way this largest wavelength behaves. On the other hand, if you look at the smallest wavelength that I have shown here, this one remains below the red line for a longer time, right? This highest one went above the red line at this epoch. This lower one had to wait for a longer time until it also went above the red line. But then the amount of time which it spent above the red line is very small compared to this one. This one spent a huge amount of time above the red line. This one spent a lot less time above the red line. And then at this epoch, it again became below the red line. And then thereafter, it continues to remain below the red line. I hope this part is clear because there is nothing very complicated about this plot. Okay, all I have done is to plot the Hubble radius as a function of time. And I said that during inflation, it's constant. Here it has slope of 2. Here it has slope of 3 halves. Both 2 and 3 halves are slopes which are bigger than 1. So it is obvious that if I plot any line with slope 1, which is the physical radius, physical wavelengths that I'm plotting, all of these lines, because they have slope less than the Hubble radius in these epochs, they will behave in this way. At some point, they will go above the red line, and at some point, they must come back below the red line. So the interesting thing about this plot is the epochs at which this going above and coming below happens. Why is this important for studying structure formation? Because remember, I told you that the Hubble radius, it behaves like a causal screen in the universe, right? Because if I have a wavelength which is larger than the Hubble radius, the amplitude of the wave mode corresponding to that wavelength cannot increase with time. It cannot evolve with time because causality prevents that amplitude from evolving. It's like frozen in time. Okay, so this plot is telling us that if I consider this particular co-moving wavelength and I look at these particular epochs, then during all of this time, the corresponding amplitude of the density perturbation for this wavelength will not grow. Okay, because this wavelength here is above the Hubble radius. On the other hand, this kind of wavelength will have a similar behavior during this epoch when its amplitude will not grow. But once its wavelength becomes smaller than the Hubble radius, now its amplitude is free to do whatever the universe allows it to do. Okay, so here gravitational evolution can take over. And finally, the last thing to emphasize in this plot is that these lower wavelengths that you can see here, they are becoming, so there is a jargon associated with this particular behavior of these wavelengths. When the wavelength becomes higher than the Hubble radius, larger than the Hubble radius, one says that that particular mode has gone outside the Hubble radius. Okay, so its size has become larger, so it has gone outside the Hubble radius. And correspondingly, when the wavelength becomes smaller than the Hubble radius, we say that the mode has entered the Hubble radius again. Okay, its wavelength has become smaller than the Hubble radius. So the thing to see here is that this small wavelength mode, it went outside the Hubble radius at a late epoch during inflation, but it entered the Hubble radius again at an early epoch when the universe was radiation dominated. Right? So in this epoch, the universe is radiation dominated and the mode has entered the Hubble radius. This particular wavelength, the larger wavelength, is something which exited the Hubble radius pretty early on during inflation, much before this smaller one. Then it waited a long time outside the Hubble radius. And by the time it could enter the Hubble radius, the universe has gone from being radiation dominated to matter dominated. Okay, so the small scale modes enter the Hubble radius during radiation domination. The large scale modes enter the Hubble radius during matter domination. And of course, by continuity, there will be a particular mode which enters the Hubble radius exactly during radiation matter equality. Okay, and that is an interesting mode also to keep track of. Okay, so this is, although it's a long discussion for one slide, it's a very important slide because if you do not understand this slide and everything that I said here, it becomes very difficult to understand whatever is happening later. Okay, so and correspondingly, when you go back and try to study these things on your own, whenever you get confused about things that are happening in perturbation theory, modes going inside, outside, etc., you should draw a picture like this for yourself, right? And it is a useful exercise to do to make sure that you understood all the concepts. Okay, so this picture I had shown you before. These are the initial conditions that we think the universe started with. So now what we want to do is to put together these ideas that we said here into actual equations and see how these equations behave and how they can be solved and what the solutions tell us in the context of this discussion of different wavelengths and their amplitudes. Okay, so we will start with the assumption that the universe at early times has very small density fluctuations. There is good evidence for this from the CMB. So it is a good idea then to try to describe the geometry of this universe as being something which is almost but not quite the same as the FLRW smooth and expanding universe, smooth and isotropic universe. So here is the metric that we want to associate with this situation where there are small fluctuations in the density field of matter and radiation. And we'll say that those small fluctuations must have caused corresponding small departures of the metric from the FLRW form. So for example, here there is this phi and psi. If I set phi and psi to 0, you will recognize the FLRW metric with conformal time written here instead of the usual cosmic time. But apart from that, it's the FLRW metric. So this phi and psi, as long as they are much less than c squared. So phi and psi have been chosen to be dimensions of gravitational potentials. So that's why they have units of velocity squared. And as long as phi and psi are much less than c squared in amplitude, this metric will be very close to the FLRW metric. And correspondingly, the matter energy momentum tensor for matter, radiation, etc. will also have fluctuations. So here I'm focusing on the matter part. That's why there's a rho bar m. So rho bar is the density, the matter density of the smooth universe. Okay, and this is the thing which would behave like 1 over a cube. And the delta that you see here is the departure of this energy density from the smooth and isotropic form. So this delta can depend on both space and time. And in addition to the density being different from smooth and uniform, the matter can also have velocities which are not tied to the co-moving observers, right? So you can have peculiar motions, and those are captured by another variable which gives you the three-dimensional velocity vector associated with any fluid element. So this velocity vector and this density at early times, at least, along with this gravitational potential, they are all assumed to be small quantities of order epsilon, where epsilon is some number much less than 1. Typically, one will say that epsilon is a number of order 10 to the minus 3 to 10 to the minus 5, depending on which fluctuations you're talking about. Okay. And starting from this metric and such an energy momentum tensor, I have not written down the energy momentum tensor corresponding to radiation. So there will be another piece similar to this, where now there will be the smooth and isotropic part of the radiation density, energy density, and the radiation pressure, which is just 1/3 the energy density. And then there will be corresponding fluctuations, space and time dependent fluctuations there as well. Okay, so in a full picture, you have to account for all of these things. I'm just showing you a simplified version of this. So continuing with this simplified version where there is only matter in the universe and radiation is not written down here, but you can include it. You can ask what are the equations, what are Einstein's equations that follow from this system, right? This is all you need to write down Einstein's equations. And then you work through the algebra, and it's a good homework exercise to try to prove these equations. So what you can see is that one of the Einstein equations becomes something that looks like Poisson equation, except that it has these extra pieces here which depend on the expansion of the universe. Okay, so if the universe was not expanding and if A is a constant, then this would just be the Poisson equation, where the Laplacian of the gravitational potential is related to the fluctuating energy, fluctuating matter density. I have also shown you here the terms which I threw away under the assumption that all these quantities are small quantities. Okay. Then another part of the Einstein equation, which you can think of as the conservation of energy and momentum, or rather the general relativistic or the generally covariant energy momentum conservation equations, those reduce to these two. So this is, it should be familiar as the continuity equation from fluid dynamics, except that the right-hand side is not zero here. The right-hand side depends on this gravitational potential suppressed by a c squared. So in the Newtonian limit, for example, you will recover the usual continuity equation of fluid dynamics. And this is a relativistic correction that comes because you're doing GR. Okay. Similarly, the Euler equation has this standard form with a piece which is related to the expansion of the universe, which creates a sort of damping effect. And on the right-hand side, I just have the gravitational force, which I would normally have written down even in the Newtonian limit. So in this case, the relativistic effects, if you ignore the fact that the expansion of the universe is playing a role, the other relativistic effects are all higher order and they can be thrown away. Okay, so this is what the system of equation looks like. And you can also derive these last two equations using the collisionless Boltzmann equation. So that is another way of arriving at this system of equations. And then you have to supply the Poisson-like equation as an extra input. But otherwise, this follows from GR itself. Okay, so these are the equations that one wants to solve. And basically what we also want to do, so here the equations are written in a little more generality than is needed, because you notice I have kept quadratic terms here. So delta times V is appearing, V times V is appearing. So if we are focusing on a situation where all of these are very small quantities, we can even ignore these pieces. Okay, so here, instead of divergence of this whole thing, I will just have divergence of V times this 1. And then here I can throw away this V dot grad V, the advective term. And this equation is anyway linear at this order. Okay, so these three equations are the ones that you want to solve, throwing away the quadratic terms. And it is not difficult to solve these things, okay, because what you can do is to just rearrange the equations, take time derivative of one of them, subtract it from the other, these kind of manipulations, and you will get a system of equations that can be at least numerically solved fairly easily. Okay. So now I'm not going to show you the result of, I'm not going to show you the exercise of doing that numerical solution, but I will show you the results. And these results are not completely, of course, you can always solve the equations numerically, but the nice thing is that under certain assumptions, in certain limits, these equations can also be solved analytically. So this plot and the next couple of plots are stolen from Dodelson's book. So I encourage you to go and read that book and the appropriate chapters if you want to study this in more detail. Okay, so what is shown here is the solution for this gravitational potential. So phi and psi can be said to be equal, and I have just shown psi here. It is the same as phi. And what is shown here is the solution for the potential phi in Fourier space. Okay, so for three different wave numbers or wave modes. So remember, these are real space equations. So this psi or phi is a function of x and t. And I can do a Fourier transform in the x space, in the 3 dimensions of x. And I can get the evolution equations for the Fourier modes phi k as a function of t. So each Fourier mode is labeled by its wave number k. And these are 3 examples of such modes with different wave numbers. And for each of the modes, one is showing the function of time, which results as a solution of these equations. So let's spend a couple of minutes on the nature of this solution and highlight a couple of interesting aspects. So firstly, what you see is that if I change the value of k, so k is 0.001 here, it's 0.1 and it's 2 in HMPC inverse units. And you can clearly see that the solutions are completely different from each other. But it is not randomly different. There is a certain order to them. Because what you notice is that the small k values, they are long wavelengths, remember. K is a wave number, right? So the wavelength associated with this perturbation is 2 pi by k. So if I take a small value of k, I get a large wavelength. Large wavelengths, if you remember this plot, large wavelengths have the behavior that they exit the Hubble radius early during inflation and they enter the Hubble radius during matter domination. So that is being seen here, because in this plot, what Dodelson has done is to show different line styles for when the perturbation is inside or outside the Hubble radius. So basically, when the perturbation is outside the Hubble radius, the line is solid. And when it comes inside the Hubble radius, the line becomes dashed. So that is very clear here. This perturbation remained, it had an amplitude which was almost constant. It decreased a little bit and it remained outside the Hubble radius until this point. You see, and then it came inside the Hubble radius and it continued to behave in the same way. Okay, it approached a constant value here. So this behavior is the behavior of a long wavelength mode which enters the Hubble radius deep inside the matter dominated era, because notice that this is the scale factor on a logarithmic scale, and what is marked here is the radiation matter equality epoch. So here you are already a scale factor which is more than 2 orders of magnitude larger than A equality. And this is where the mode is entering the Hubble radius. So this is the solution that you get for modes which enter the Hubble radius, which remain outside the Hubble radius for all of this period. And then they enter the Hubble radius when the universe is matter dominated. Okay. In contrast, look at this mode, which is, as far as you can see on the plot, it is always a dashed line. And actually what has happened, if you calculate the numbers for this example, the entry into the Hubble radius is almost at the edge of the plot or even before. So it's actually probably around here. Okay, so the mode entered the Hubble radius here already, when the universe was completely radiation dominated. And you see that qualitatively, its behavior is completely different from this mode which entered in matter domination, because the amplitude of this potential rapidly decayed. And then it settled down to, it did some few oscillations, and then it settled down to a constant value. During matter domination, the mode became constant, okay? And its constant value is determined, it's very close to zero for this example, but it's basically determined by how far it could fall after entering the Hubble radius during radiation domination. And this feature is also made more clear by this intermediate mode, which entered the Hubble radius somewhere around here, okay? And the universe was still radiation dominated, so it started decaying, but now it didn't have that much time to decay, because by the time it decayed by a substantial amount, the universe became matter dominated, and this mode was forced to become a constant, okay? So the nature of the equations, when you work them out, is such that any mode, if it is being studied during the matter-dominated epoch, its gravitational potential will be a constant. Okay, the value of the constant will depend on whether or not that mode has entered the Hubble radius or not. So a mode which has entered the Hubble radius during matter domination will have a value which is substantially higher than the modes which have entered during radiation domination and have evolved like this. They have decayed a bit and then they became constant during matter domination. So this is a very important fact about the nature of these solutions, which decides a lot of interesting things in cosmology, as we will see in the next few slides. Okay, so what you have to take away from this slide is the fact that the gravitational potential, it freezes during matter domination, but the value to which it freezes depends on the wave number that you're talking about. The lower wave numbers, which correspond to long wavelengths, they freeze out to larger values, and higher wavelengths, higher wave numbers corresponding to smaller wavelengths freeze out to smaller values. Okay, so there is a hierarchy that is developed in the amplitude of the gravitational potential as a function of scale. Now you can also ask the same question from a different point of view. Gravitational potential is fine, but I am interested in studying the density of the matter, right? So how do the density fluctuations behave as a function of time? Here again, you can go through the same logic as before, and you will find that in this, for such modes, the density perturbations grow very slowly. Even during radiation domination, they will grow, but very slowly, logarithmically only. Thereafter here, they will start behaving like whatever the modes are supposed to do when they have become smaller than the Hubble radius. We will see that in a second. And these modes for which the wave number is very low, they will remain completely frozen, and then their behavior will only start kicking in at much later times once they enter the Hubble radius. And here they will again behave in the same way as these modes. And this behavior is seen here. So these are the same three modes or very similar modes, but now shown from the point of view of the density contrast as a function of time for each of these modes. And what you can see here, for example, is that this small scale mode, which corresponds to, sorry, I'm getting this wrong. So this is the small scale mode, which corresponds to a very high wave number. This is the one for which the gravitational potential decayed quite a bit and then it froze out here. So the density contrast for this during radiation domination, it will have some kind of growth, but once it enters the horizon, it will settle down into a more or less linear growth with scale factor. Okay, so this is the place where that mode entered the Hubble radius. This intermediate mode entered the Hubble radius much later, so it remained pretty much constant, and only after entering the Hubble radius, it has started growing. And this mode remained outside the Hubble radius for a much longer time and has only entered during matter domination, and then it has started growing. And this growth actually of these individual modes, the function of time that you get, you can prove is actually the same function for all of them. It's just that their amplitudes are different. Okay, but the evolution as a function of time is the same. It is given by the so-called growth factor, which comes out as a solution to this second order differential equation. So this is not anything mysterious. It is the same equations that I was showing you here. basically what you say is that first you throw away all the quadratic terms, right? So then I'll have derivative of delta plus divergence of v. Here I'll have derivative of v plus h times v. So I can take a divergence of this equation and I will get time derivative of divergence v plus h times divergence v is equal to Laplacian of psi. Laplacian of psi I can get from this equation. And I am working at late epochs where actually these two terms you can ignore, because psi will become approximately a constant and this h squared psi will be much smaller than Laplacian of psi. Okay, so this will just become the standard Poisson equation, Laplacian psi equal to delta. So I can plug in that dependence here. Okay, so this Laplacian psi, I can, when I take divergence of this equation, I will get a term proportional to delta. And here I will have time derivative of divergence of v. And here I have divergence of v already appearing from this term. So I can take a time derivative of this equation. So now I'll get two derivatives of delta and I'll get time derivative of divergence of v, which I can replace from here. Okay, and then I'll have Laplacian of psi, I'll have a divergence of v. Divergence of v I can again replace in terms of time derivative of delta. So these are manipulations that you can very easily do. It's just algebra manipulation, jugglery, and you will get this second order differential equation. This is the equation satisfied by all the Fourier modes as long as they are inside the Hubble radius. The wavelengths are inside the Hubble radius. And in order to see what the solution of this looks like, you can actually prove very easily that one of the solutions, see, it's a second order differential equation, it has two independent solutions. One of the solution is always proportional to the Hubble parameter itself. It's a very simple exercise to say let delta be proportional to h, write out all of the derivatives and apply Friedman's equations, and you will find that this equation here is actually satisfied. So delta proportional to h is a solution of this equation, but it's not a very interesting solution because h as a function of time is a decreasing function in these epochs, right? Because this is matter dominated epochs that we are talking about. So this is a decaying solution because it decreases as a function of time. So for the other solution, which is the solution of interest, it's useful to look at this equation during matter domination when h is proportional to a to the power minus 3 halves. So this equation becomes the same as this equation. And here it's very easy to see that if I set delta proportional to a, then this term will drop out because there's two derivatives. Here, this term will give you just a 1. So let's say I say delta equal to a. Okay, and don't worry about the amplitude. So delta is equal to a, this term is 1, this term is a. So this is 3 by 2a minus 3 by 2a squared times a. So this is 0. So this equation is satisfied by delta proportional to a, which means that this growth function in this regime of matter domination sub-Hubble modes, the growth of fluctuations in the linear regime is proportional to the scale factor. This is a very, very useful piece of information because it tells you a very simple model which is exact in this particular limit of linear perturbations for how structures form because the density grows proportionally to the scale factor. So I know I've gone a bit fast, but all the equations are there and the recording is there. You can come back and look at this at your own pace. So now let's look, we are running short of time. So let's look at putting these things together. And what you can now do is to say, okay, after all this evolution has happened, right? I start from inflation, I go through this tiny perturbations, and then I let the universe become radiation dominated, then it becomes matter dominated. What I'm finally interested in is if I look at the sky today, and I can somehow measure these density perturbations in the sky, what power spectrum should I see for these perturbations? And you can put all these calculations together and you'll get a power spectrum that looks like this. So this has a very characteristic feature. It has increasing, so this is, remember, the 2-point function now of the matter density fluctuations in linear theory. So at low k values, which correspond to long wavelengths, this has a characteristic behavior which is increasing as a function of time. And in fact, you can convince yourself that if the gauge invariant curvature perturbation zeta, which is actually nothing but the gravitational potential in the way we wrote down the metric, if that has a power spectrum which is k to the power ns minus 1, then this p of k, so remember that had a power spectrum which was k cubed p zeta is k to the power ns minus 1. So you can work through the algebra and use Poisson's equation, Laplacian psi equal to delta, to convince yourself that the pk associated with delta must have a form which is k to the power ns. And we said that ns is close to 1. So this should be p of k approximately proportional to k for modes which have not been affected much by structure formation. They have just retained their original primordial power spectrum. Okay, so this is the primordial part of the power spectrum for modes which are whose wavelengths are so large that they are just now entering the Hubble radius, and their power spectrum looks like this. On the other side, you have these modes at which the power spectrum is steeply falling as a function of k. And this is not very difficult to understand from the fact that the potential decays very rapidly, and the amount by which it decays increases if I increase the wave number. So this is a lower wave number, this is a higher wave number. This decay compared to this value is much less than this decay compared to this value. So as I keep going to higher and higher k, I am effectively traversing this plot downwards. So imagine making a snapshot of this plot exactly at a equal to 1, which is what is being done there. And you can convince yourself that this should be a decaying function, like a decreasing function. And in fact, you can go one step beyond and you can actually calculate the power law according to which this should decay. Okay, and it will turn out that this is some k to the power -4 or so, and modulated by a log k, etc. So this is analytically provable that this decay should happen here. And now it's just based on continuity, you can argue that this is the primordial part which is increasing. This is the part which has been processed by the radiation dominated epoch. So here the power spectrum is decreasing. And in between, therefore, by continuity, there should be a place where the power spectrum has the maximum power. And you can also convince yourself that this maximum power happens precisely at the wave number corresponding to the mode which entered the horizon, the Hubble radius during radiation matter equality. Okay, it was this particular, so some wave number which entered exactly around the radiation matter equality. That is the one which will end up having the maximum amount of power. And this is a very, very useful thing observationally, because now if you have a way of trying to measure this power spectrum in data, you can look for such a maximum. And for example, what you can see here is that depending on the choice of cosmology, the location of this maximum changes. Okay, and that's simply the fact that the radiation matter equality epoch responds to whether or not I have, so how much omega matter there is in the universe. Okay, so in the standard CDM model where omega matter is 1, the radiation matter equality epoch will correspond to a wave number here. And in lambda CDM, because omega m plus omega lambda is close to 1, so omega m is less than 1. It's about 0.3 or so in the standard model. And then the corresponding wave number will shift to lower values. You can prove this. Okay, and therefore the location of this bump or of this maximum is a very useful observational probe of whether you are in a standard CDM model or lambda CDM model. And in fact, this was one of the earliest evidences for the presence of lambda. Even before supernova cosmology came into its own in the mid-90s, in 1991, there was a paper by Eustathiou, Sutherland, and Maddox, in which they argued that the observations of large-scale structure were indicating that the value of omega matter has to be firstly less than 1, which was also known from cluster studies, but also that the structure formation power spectra are consistent with a universe in which omega lambda is the one that is causing a departure of the, it is causing the, so the total density parameter of the universe is unity, but omega lambda is making up the difference, and it is not because of a curvature. Okay, so this is just a historical piece of interesting fact. This is another way of writing down or showing the linear theory power spectrum. Here, instead of showing P of k, I have shown this dimensionless quantity, delta squared, and taken a square root. And this plot is stolen from this particular paper. And in this case, you will see that when you do this, the sharp decrease that you saw here, it mostly goes away because of this k cubed. And you are left with a slow logarithmic increase. Okay, so that power law is actually k to the -3 times log of k the whole squared. And when you multiply by k cubed, the k to the -3 goes away and you're left with this increase. So in a purely cold dark matter cosmology, this increase would continue forever. But that is an unrealistic model, because we expect that any model of dark matter that comes from particle physics, for example, must have a scale below which there are no perturbations, because there should be something called the free streaming of matter below this scale, which is something you would have seen in the thermal history of the universe also, if the formation of dark matter was, or possible formation of dark matter was discussed. And if you are interested in the reason why this kind of cutoff happens, you can talk to me later. I'll just mention here that these are hypothetical models of what is called warm dark matter, in which the dark matter particle mass is chosen to be 1 keV or 10 keV according to the line styles, and depending on this choice, the power spectrum has a sharp truncation. But for a typical cold dark matter universe, in which we expect, for example, that the mass of the particle that is forming dark matter, if it is something like 100 GeV WIMP, then it's much, much larger than 10 keV. So this solid line will just keep going for a very long amount. Okay, so this is linear theory. And now in the remaining part of the talk, let me just quickly discuss what happens beyond linear theory. So I will just give you a flavor for the way people think about the growth of structure beyond linear theory. So like I said, once you go beyond linear theory, it becomes very difficult to solve these equations. In fact, the equations, the way I showed you, don't even remain valid once the structure becomes very nonlinear, because something called shell crossing or multi-streaming happens. And if you're interested, you can ask me later. And basically that fluid picture of the universe, you have to discard it in favor of a different way of thinking. And this way of thinking is what is called the Lagrangian approach, where you say that I will follow individual fluid elements and I will ask how they behave. So the simplest picture of this Lagrangian approach is the spherical collapse model, where I say that I will follow a shell of matter which is spherically symmetric, and I will assume that all the inhomogeneity in the universe is spherically symmetric around one point, which I choose to be the center of the universe, where I place myself. It's a completely fake universe. The real universe is not like this, but it's a useful toy model because it allows you to study nonlinear structure formation in great detail, because it's a completely analytical model. The reason it is analytical is because of this fact that in the Newtonian limit, GR and Newton's theory are identical. So, and that is true of cosmology also. If I come to very small scales, where I am interested in studying nonlinear structure, the equations that I need to solve are essentially the same as Newtonian gravity. It's just that the initial conditions have to be adjusted a little bit carefully, that's all. So in Newtonian gravity, you remember that if I have a shell of matter or if I have a piece of chalk, it doesn't matter. As long as, I'm standing on a spherically symmetric earth and I take a piece of chalk and I throw it upwards, its trajectory, that is its height as a function of time, will be governed by this equation, right? Because it's just acceleration given by Newtonian gravity, a gravitational force. So the same thing applies here also. Now I have a shell of matter, which is initially given some initial kick, for example, and now I am just asking how its radius changes as a function of time, and its equation is exactly the same. Actually, its acceleration is completely determined by the mass that it is enclosing. We know how to solve this equation. It gives the standard cycloid solutions. If you remember your 12th standard gravitation lectures. So that same solution one can write down here. And remember, you can parameterize this solution in terms of a variable theta, which varies from 0 to 2 pi. And now, basically, I will get a solution that looks like this cycloid. Okay, so now in this solution, the nice thing is that I can write down everything analytically, because I know R as a function of time, parameterized by theta. So I can also write down the density of this shell, or density enclosed inside this shell as a function of time, or the mass enclosed inside the shell, which is a constant. So I can calculate the density. So because the mass is a constant, the density is just 1 over r cubed. And as a function of time, if I divide by the mean density of the universe, which is just given by the Hubble squared, and Hubble squared is proportional to 1 over t squared. So that just gives you a t squared in the numerator here, that's theta minus sine theta, and r cubed in the denominator. So that's 1 minus cos theta cubed. So this density, for example, will behave in a certain way. It will start off being increasing according to linear theory. And eventually, when this theta approaches 2 pi, this 1 minus cos theta will go to 0, and this density will become infinite. And that will happen at a finite time, because at the time when theta approaches 2 pi, this t will remain a finite number. Okay, and at the same time, this radius will go to 0. That is why this density is becoming infinite. So that is this cycloid. At a finite time, it goes through a maximum, then comes down to 0. And then let me not discuss this part, although it is interesting. We will not discuss this, but this is just to say that at least in such a model, you can follow the growth of the density well into the nonlinear regime. In fact, all the way down to infinite density, which is unphysical. So in order to remove this unphysical nature, one has to do some other assumptions. For example, you assume that this blob will virialize and it will reach some kind of equilibrium, which will be determined by the virial theorem. And you can ask, what is the radius that this blob will achieve when the virial theorem is satisfied? And it will turn out to be 1/2 of the radius at turnaround. And all of these are numbers that you can calculate very easily in this model. Okay, so this is one way of thinking about nonlinear structure formation. Another way is also an old way. So this way, the spherical collapse was something that was developed in the mid-70s also. And this second thing is another way of thinking about the formation of structure, which also goes back to a similar time, 1970. It was developed by the Russian physicist Zeldovich. And what he said was that let's think from the point of view of individual fluid elements and study these elements as if they were behaving according to linear theory. Meaning their motions, let us assume, are governed by linear theory. But we don't assume that the density is going according to linear theory. We will just give all of these blobs initial kicks and just set their velocities equal to a function which depends on the linear theory solution. Okay, so it's a very cute ansatz because it allows for the density of the universe to become arbitrarily large without actually solving any of the complicated equations of nonlinear gravity. Okay, so of course, it's not solving the exact equation, so it cannot be an exact answer, but it is remarkable to see that this very simple ansatz, where you say that I have just an initial vector, which is determined by the Gaussian random field, which was generated by inflation. And then the time dependence is given by linear theory. So this is straight line motion because the direction of the vector doesn't change for any fluid element, only the amplitude of the velocity changes. This already creates a form of the final density contrast, which looks very similar to the results of n-body simulations. Okay, so this movie was created by a student at IUCAA, Sujata Ramakrishnan, who coded up this Zeldovich approximation in a computer, generated initial conditions randomly, and allowed these initial fluid elements to evolve with time according to this straight line motion. And you can see that this picture looks pretty similar to the kind of simulation that I was showing you before. So this is another very useful and powerful ansatz, and it has been very widely used in the literature for a variety of applications. So this was a very rapid fire introduction to nonlinear approximations. And let me also give you an equally rapid fire introduction to simulating the universe using full-fledged n-body simulations. Okay, so here what you basically say is that I don't know how to solve these fluid equations exactly, but what I can say is that I will think of this fluid that I am talking about as something which has a phase space distribution structure. So phase space is something that you also saw, I think, in the thermal history part of the earlier lecture course. And this phase space distribution depends on position and velocity. So basically it says that as a function of position and velocity, what is the number count of particles, number density of particles. And this distribution function, if we know how it evolves for something like dark matter, then you can integrate over velocities and you can get the density field of dark matter. So we would like to solve the equations governing this phase space distribution function. And these equations for cold dark matter is the collisionless Boltzmann equation, supplemented by the Poisson equation for gravity. So this is what you want to solve. So instead of solving this equation, which is very difficult to solve numerically, it will probably not be solvable in the foreseeable future at the resolutions that we want. So instead of doing this, what you say is that I will sample this phase space distribution with particles, with tracers. So I will just give equal mass tracers at different places in this distribution. And I will ask if these tracers contained all of the mass of their neighborhood, how should they evolve as a function of time? In the sense of where should they be and what should their velocity be as a function of time? So I want to solve for the positions and velocities of tracers of the phase space distribution function. So that is what is summarized here. We want to solve the collisionless Boltzmann equation with cold initial conditions. And the approach is to sample phase space distribution function with tracers or particles and follow their positions and velocities as a function of time. And the equations governing these positions and velocities are actually just Newton's law along with the Poisson equation. Okay, Newton's law for acceleration is equal to gradient of potential. That is all that you need to solve. Okay, and then there are some technical details about how to solve these things properly, because these particles are not fundamental particles. They are blobs, which are determined, the size of these blobs is determined by your computing power. How many such particles you can place in a cosmological volume determines the mass of every particle. So it is routine to perform simulations where every individual so-called particle is actually the size of a galaxy. Okay, so these are not really particles. They are just big blobs. They should be thought of as representing fluid elements. So when two such blobs come close to each other, you don't want them to collide like billiard balls. Okay, because that is not the correct system of equations that you should be solving. So there are these technical issues about how to avoid this. It is called force softening. I can discuss this in detail later if you want. And then there are other even more technical aspects of actually how to run these simulations fast. Because it's an n-body problem. So the scaling would be n cubed in 3 dimensions for calculating these forces, which you don't want to do. So you want to bring it down to something like n log n. So you need to combine Fourier techniques and tree-based calculations in order to speed things up. Okay, and then one has to worry about other things like convergence of your results as a function of the number of particles that you put in and so on. But now, so this started in the mid 80s, this technology, and computers developed and coding techniques also developed. And today we are in a situation where even theorists like me can take publicly existing codes, which the coders have very kindly made available, and you can run simulations on a reasonable sized cluster of, at IUCAA, for example, the cluster that we have is capable of running a fairly decent set of simulations. And the outputs of these simulations, this is my last slide, are basically things which relate to the formation of structure. So for example, I was talking about spherical collapse, where at the end there is a blob which is forming, and we say that it must have virialized and stabilized. So these virialized, stabilized blobs, they are given a name in cosmology. They are called halos of dark matter. And the structure of the cosmic web is such that there is a hierarchy of these halos. So you can have a big halo, and then inside that big halo, you can have smaller halos which have their own identity, but they are orbiting inside the smaller halo, inside the bigger halo, and so on. So what one typically studies, for example, is the distribution of masses of these halos, the halo mass function, which is shown here, or the subhalo mass function, which is, or the growth of, subhalo mass function is shown here, or the growth of these halos as a function of time, how they accumulate mass as a function of time, which is shown here. And something that we were discussing before, the power spectrum of dark matter in such a non-linearly evolved system. So that is shown here. For example, here it has been divided out by some convenient functions to show you some details, but basically just take away this fact that this dotted line is showing you what linear theory would predict, and these data points are the results of n-body simulations. And what you can see is that at low k values, large length scales, the linear theory prediction is a pretty accurate description of the simulation. But as you go to higher k or smaller wavelengths, where I have nonlinearities kicking in, there I see that the power spectrum in the simulations, it departs from linear theory, and I have more power at small scales. Okay, and then these solid lines are some ways of analytically trying to describe the results of these n-body simulations. So this is what I wanted to say today. I realize it has been a bit fast, but I can take questions if there are any. So I have opened my window. I can also just check quickly if there is anything in the Google Sheet. Yesterday there was nothing, there is still nothing. So if you have questions, maybe you can just raise your hands. Otherwise, it is already over time. Okay, I see some, yes, unique. This is a very familiar name. I think you were here last year also. Okay, you can ask your question, please.
Hello, sir. Am I audible?
Yes, yes.
Thank you, sir. So my question was regarding the first part of your lecture where you are showing the growth of the structure curves. That is the three different wavelengths. So when they are entering the Hubble radius and they were exiting from there, the curve that was before this one. Yeah. So there, you have pointed out the inflation ends on.
You mean this one?
Yes. This one.
Okay.
So he mark the points where the inflation ends and the radiation-dominated era starts,
Yes.
and further the radiation-dominated era ends and the matter-dominated era starts. So my point is, how can we fit this data along with the dark matter-dominated era at the same time? What will the nature of the curves in that case?
No. So dark matter domination or matter domination is this part, right? This is matter domination. This is radiation domination. Here to here is radiation domination. Then radiation matter equality happens, and after that, at higher time, later times, matter domination happens. So this is radiation domination where the Hubble parameter goes like 1 over a squared. This is matter domination where the Hubble parameter goes like 1 over a to the 3 halves. So that is why H inverse is like a squared here and a to the 3 halves here. So a squared is steeper than a to the 3 halves. So does this answer your question?
So the matter-dominated era means both dark matter as well as our regular baryonic matter, the complete matter dominant.
Yes, of course. Because you see, dark matter makes up most of matter anyway. So when you say omega matter has become larger than omega radiation, or rho matter has become larger than rho radiation, you are counting in matter all the non-relativistic species that contribute. So dark matter is the dominant component actually there. Dark matter is roughly 5 times larger than 6 times larger. 5:1 ratio, right? Roughly.
Okay, sir. And sir, I have a second question. May I ask?
Okay. Yeah, go ahead.
Sir, on this basic slide only, the first part you have explained that the Hubble radius remains constant while the inflation part. But sir, as per approximately. Yes. But sir, the Hubble radius isn't like it is expanding during the inflation, during the inflation part.
No. So remember, we were talking about inflation yesterday, right? And the idea was that the way standard models produce inflation is using this single field slow roll, where you have. So remember, with the single inflaton field, which is homogeneous and isotropic, rho is phi dot squared by 2 plus v of phi. P is phi dot squared by 2 minus v of phi. And my v of phi is almost a constant. It's a flat potential. So phi dot is very small. So rho is approximately v of phi. P is approximately minus v of phi. So P is approximately minus rho. So that is like a cosmological constant. Okay, almost. And you know that if I have only a cosmological constant in my universe, then the Hubble parameter is a constant, because h squared is just rho, right? And rho is almost a constant. So h is almost a constant. It's the scale factor which changes exponentially. When h is constant, a dot by a is constant. So a goes exponentially like t. If you do not understand this, you have to go back to Surut's lectures and work through the answer.
Yeah. I got this. Thank you, sir.
Okay, so let's move to the next person, Shriya.
Good afternoon, sir. Am I audible?
Yes.
Sir, my question is from the graph of the power versus K. Could you please explain the physical significance of this curve? What this maxima and the degradation shows physically signify?
So physically what it is saying is that, you see, so remember this power spectrum is measuring how much the density contrast is changing, right? So what variation there is in the density contrast. So if I focus only on high frequency variations, so maybe I can go back to the previous talk where the Gaussian random field was shown. Okay, so for example, here there are some high frequency variations which are not there in this one, right? You can see the difference, right? So here this part is going up and down quite rapidly by a larger amplitude than it is doing here, correct? Yes. And similarly here you see this part is relatively smooth here and this part is going up and down. You see that, right? So this is saying that there are two things to take away. First thing that you can understand is that what is the difference between this and this? The difference is that I added some high frequency modes here, which were not there here. So the fact that there is some kind of variation with high frequency means that there is a non-zero amplitude for these high frequency modes. Okay, that is step number one. The second thing is that value of the non-zero amplitude is a pretty small number here, right? Because the amount by which I am going up and down at these high frequencies is not as big as the amount by which I am going up and down at low frequencies. See, at low frequencies, I am going up all the way to 0.4, minus 0.6, plus 0.4, right? But at high frequency, I am only going up and down by maybe like 0.05, 0.01, and so on, correct?
Yes.
And in fact, if I go to an even earlier plot, here, my high frequency modes are again there in the lower panel, but they have much higher amplitude. In fact, their amplitude is almost as large as the low frequency amplitude. Here, the low frequency modes are going up and down by plus minus 1 or 2, but the high frequency modes are also going up and down by plus minus 1 or 2. Okay, so if you appreciate this difference, then you can also appreciate the difference here. So for example, here, these particular modes are low frequency modes, if you like, right? And these are high frequency modes. So this is saying that the universe has more power at these low frequencies than at these high frequencies. And the physical reason for this is what happened during radiation domination. Because see, during radiation domination, radiation was dominating. Okay, what does that mean? The Hubble parameter was a high number, right? H was a large number, and it was radiation which was driving the expansion of the universe. So you can physically imagine a situation where the expansion is like very, very rapid, and like radiation is pushing everything away. And now on top of this very smooth and very rapidly expanding radiation, right? Radiation is traveling at the speed of light, right? And it is pushing the expansion of the universe. On top of this, I have ordinary matter, whose fluctuations are trying to attract matter and trying to grow as a function of time. But this growth, because of attractive gravity, it has to counter the effect of this rapid expansion due to radiation. And for modes which were trying to grow during radiation domination, right? So for these modes, the ones which entered during radiation domination and they suddenly realized, aha, we have entered the Hubble radius, now we can grow, let us grow. But they find that the universe is dominated by radiation. So they cannot grow as fast as they would like to grow. Okay, and that is why they remain suppressed as compared to these other modes which entered a bit later. And as soon as they entered around the time of radiation matter equality, they did not have to suffer this damping due to the expansion caused by radiation domination, right? And then their growth was much less suppressed. So physically, this is one way of understanding. Was that okay?
Yeah. Yes, sir. Yes. Thank you, sir.
All right. So Unique has another question, or is this your old hand? Okay. I guess there is no other question. Okay, so we are well over time. So maybe we can end the meeting here and we will speak tomorrow.